Hello dear student, this is Devang Shah from LJ Institute of Engineering and Technology. So in our previous chapter, we have discussed about the DC circuits. Now welcome to new chapter which is called AC circuits. Now why we need to learn this AC circuits? Just we here need to compare what we have learned in a DC circuits, right, where you learn about the basic components resistance, inductor and capacitor. You have applied the DC source and you check the behavior of resistance, inductor and capacitor in a various situation. Now same thing here we have to do. We have to apply the same terminology where resistance, inductor and capacitor is there, and where resistance, inductor and capacitor are there, and you have to apply AC voltage to resistance, inductor and capacitor, and you have to check the behavior of resistance, inductor and capacitor. Now, so once you apply the AC signal to resistance, you have to check only resistance, behavior of only resistance. Then you have to check the behavior of only inductor, then you have to check behavior of only capacitor, then you have to do it everything in a combination, like you have to check the behavior of RL, RC and RLC like this way. So AC circuits using the resistance, inductor and capacitor, my first job is to understand what is AC, what is alternating current, or what is AC signal, right. So you can see a resistance, inductor, capacitor. You also learn about the voltage sources, right. Now the first important term where you have to find this alternating quantity, where here the alternating parameter, maybe it is a voltage or it is a current, right. So it's a part of our subject basic electrical engineering. You can check here in a AC circuits, this particular this following points we have to learn with the representation of sinusoidal waveforms, then peak and RMS values, phasor representation of this AC quantities, real power, reactive power, apparent power and power factor. This is the first phase, and in another phase we have to do a little bit analysis of this AC circuits, like analysis of single phase AC circuits using only resistance, only capacitor, only inductor, then the combination of resistance and inductor, same with the combination of resistance and capacitor, and a combination of resistance, inductor and capacitor, right. Same way we have to connect all these three components in series and parallel, and what happen at the resonance condition of this series and parallel RLC circuit. So throughout the chapter we are going to learn all this particular topic. So we'll start with how we can generate AC signal. So before that, little bit discuss about the alternating quantity. So it's a common question, like you already learn about the DC. Now what should be the difference of AC and DC here, right? So you can find here DC, that is always a constant in a magnitude and direction, right. So once you connect any resistance in a circuit with the DC source, that means current forever is flowing in a one direction, right. So current always in a unidirectional forever at t tends to infinite, but this is not case with the AC, as it is alternating current, right. So once you connect any resistance and you apply the AC source, that means current will be flowing in a bidirectional. So for a certain interval of time, let's say for 0 to 2 second, current is flowing in a clockwise direction, and from 2 second to 4 second, let's say current is flowing in an anti-clockwise direction, right. So that's how the current is changing the direction. It's alternate, one is clockwise, another one is anti-clockwise, right. So same way you can see here magnitude and direction continuously changing with respect to time. So these two are the AC and DC, right. Now again in a you can check here, these are the different examples of AC signals, like one of the signal is a sinusoidal signal, another signal is a square wave signal, where it shows the magnitude of this signals are alternate. For a certain period of time it is positive, for a certain period of time it is a negative. You can further check with the triangular wave, complex waves, right. So all are changing its magnitude with respect to time, right. The next one, we can here need to understand why we are going for AC. Is there any advantages of AC than that of the DC. Yes, there are various advantage of AC, and you can see our household application, all home appliances are operated on AC signals, right? So you can observe at your home, television, fridge, microwave, oven, washing machine, all are working, air conditioning, all are working on a AC signals, right? So what are the advantage of this AC signal? One of the advantages that you can adjust step up and step down possible using the transformer. So transformer is working on a only AC signals, right? So it can be useful in a transformer. Same way, high voltage transmission is possible through the AC, but DC it is not possible. Why? Because the wastage of voltage drop in terms of the DC is very high, right? So transmission can be possible here. The simple and robust construction of AC motor is possible. So here we can construct AC motors, alternators, all are based on a AC signals, right? Again, we can go for a rectifier circuit. Again, it's a possible build up voltage of a low cost generator. Everything is working on a AC signal, right? So all these advantages are related to AC signal. So that's why we are using the AC signal in our more than 80% household applications, right? Now you can check here how we can generate this alternating induced EMF. So let's discuss about the Faraday's law of electromagnetic induction. Right now, this is what the principle behind a generation of electromotive force or generation of AC signal. Right, where there are two magnets are connected. And there is a space in between, where if you make this arrangement, one is a N pole, another one is a S pole. So in between there is a production of magnetic flux, right? Now you take a simple conductor rod and passing like this way, you can passing like this metal conductor in between. So here the magnetic flux which is being induced because of this two magnets is now is going to cut, right? So once the magnetic flux is being cut, this will generate an EMF as per the Faraday's law of electromagnetic induction, right? So here the EMF will be E is equal to d phi divided by dt, where phi is called the magnetic flux, right? And after that, Lenz has given that whatever EMF is going to be generated, which is always in opposite direction of applied force. So here by this electromagnetic induction, Faraday's law, here there is a generation of EMF, right? So in another sense, you can consider as if you want to generate a EMF, you must require two kinds of magnetic fields. One magnetic field is defined as a static magnetic field. So here in this case, these magnets are static, are fixed. So this will generate a static magnetic field, right? But here the metal object, here this conductor object is continuously moving, so that will generate dynamic magnetic field, right? So always remember, to generate AC signal, to generate this alternating signal EMF, you have to combine static magnetic field and dynamic magnetic field, right? And that is represented as the Faraday's law of electromagnetic induction, right? So here in our job, where this particular conductor is moving linearly, now we are going to take the same conductor, but they should not move linearly, but that should move angular motion, right? So you can see here. Now in real case, how we can generate a AC signal? So again, there are two magnets having N pole and S pole facing with each other. In between there is a space where you have to put the wire loop. It's a one kind of conductor which is continuously moving in an anti-clockwise direction. Now here two magnets, N pole and S pole, in between there is a production of magnetic flux. So that particular terminology we define as the static magnetic field, where my next job is to generate a dynamic magnetic field by putting metal loop or a wire loop. It's a kind of conductor which is moving in an anti-clockwise direction between these two magnets. So this particular loop is continuously moving, so that will generate dynamic magnetic field, right? So combination of these two, that will generate EMF or electromotive force, which is a AC quantity. So here N having the N number of turns of coil, right, where A is defined as the area of the coil, which is always in a meter square. Then the conductor is rotating in an anti-clockwise direction with the angular velocity of omega, and the whatever magnetic flux is being generated, that we define as a phi. So here once the magnetic flux is produced, the maximum value of that magnetic flux we define as a phi m, right, that is in a Weber. You can see here from this, look from the side view, this particular conductor is moving in an anti-clockwise direction with the angular velocity of omega. See, it's continuously cut the produced magnetic flux, and once it will cut the produced magnetic flux, here there is a Faraday's law of electromagnetic induction applies, and that will generate EMF, right. So how it will generate a EMF? Before that, let's learn how here you will find, or how it will generate alternating magnetic flux, right, once the conductor is moving in an anti-clockwise direction. So you can define here different positions, like position x, x dash, y dash. You can also categorize into 0 angle, 90 angle, 180, 270 and 360. Why? Because this conductor is moving in a rotational direction. So it will first start with the 0, then come to 90, 180, 270 and 360. That will have a complete one revolution. So in between you will phi is equal to phi m cos omega t, right. When it reaches to x, x dash, that particular axis, it will find phi is equal to phi m sin omega t, right. So once you put the omega t, it's nothing but the position of this angular velocity. The angular velocity is nothing but the angular displacement divided by time. So from that you can find the angular displacement theta is equal to omega t. So ultimately, once this conductor is moving in an anti-clockwise direction, rotating in anti-clockwise direction, that will attain the angular positions of angle 0, 90, 180, 270, and that will again come to 360. Once you apply in this particular equation, you will find the produced magnetic flux phi, which is once it touches to x, x dash, that will have the minimum value of 0, and once this touches to angle 90, it has a maximum value of magnetic flux. So phi is equal to phi m. So by that way, throughout the complete rotation, if you find the value of flux, that is alternating. So right, so at one position you will find 0, another position you will find a maximum. So if you apply here the Faraday's law of induction, that produced EMF E is equal to minus n into d phi by dt. So phi equation, if I consider phi m cos omega t, and if I taking the derivation of this term, I will find E is equal to Em sin omega t, where Em is called the magnitude, and that Em is defined as n into d phi into n into phi m into omega, Em sin omega t. So it here in equation E is equal to Em sin omega t, so sin itself representing the alternating condition, right. So once you are taking the different angular positions of omega t, like here again we repeat this portion where E is equal to minus n into d phi by dt. Same way you will finally going to have the equation of E is equal to Em sin omega t, where Em is represented as a magnitude, that is equal to n into phi m into omega. N is the number of turns of the coil, phi m is equal to Bm into A. Bm is called the maximum flux density Weber per meter square, A is defined as the area, and angular velocity omega is equal to 2 pi f, right. So here if we plot this E is equal to Em sin omega t throughout one complete revolution of this conductor, you will find this kind of waveform, which is a sinusoidal waveform, right. So again mathematically, if you want to prove, then you can prove like this: E is equal to Em sin omega t, where you are taking the different phase angles, omega t is equal to angle 0, and that particular omega t is equal to 0, you put in above equation E is equal to Em sin 0, that E is equal to 0, right. Now omega t you take 90, right. So first my position, when my conductor start at angle 0, at that time omega t is equal to 0. So the position is at having at angle 0. So the induced EMF is also equal to 0. When this conductor is moving in a 90 direction, right, here omega t is equal to 90. So once I write this equation, omega t is equal to 90, in above equation E is equal to Em sin 90, where you will find the maximum value of amplitude E is equal to plus Em. Same way it reaches to 180, again omega t is equal to 180, that means E is equal to 0. So you can straight away see this conductor is a arrow, this between two magnet, and this is start the journey from angle 0, 90, 180, 270 and 360. Likewise, if you put this omega t values in above equation, you will find 0 plus em, again 0 minus em and 0. So if you want to plot all these values, you can straight away find this waveform where at angle 0 the value of E is equal to 0, at angle 90 the E is reaches the maximum value which is plus Em, then minus Em, and again it will come to 0. So this quantity is again alternating quantity. So by this way you can generate a AC signal simply by applying the Faraday's law of electromagnetic induction, right. Thank you very much, dear students.